Okay, so what I am going to elaborate today, given exposure to, is a tool known as randomized rounding. Okay, so it is a way of converting, it is a way of getting integral solutions or discrete solutions from fractional solutions. So we computer science, theoretical computer science, yeah? No, he says it is meant for the video recording. So if you are not able to hear, then I will speak a little louder, okay? So it is a way of getting integral solutions from fractional solutions, okay? A number of problems in TCS are basically discrete optimization problems. So the solution space is a set of what we call integral vectors. Okay. So the general framework is the solution space would be a set of integral vectors. That is set of say something like this Zn, set of all integers. You take the n-dimensional vector over these, and what we want is, we want to get this, and several of these can be framed as an integer linear program, but integer linear program is NP-hard, because all of these NP-hard problems, several of these NP-hard problems can be framed as an integer linear program. So what you do is you relax these integrality requirements and allow fractional solutions also. Then what you get is linear program. Linear programs are efficiently solvable, at least in theory, by the results of Kajian, and in fact in practice also by the result of Karmarkar and simplex method. And then what you do is you treat these fractional solutions and treat the vectors. Typically you will be focused on solutions being, in fact, solution space being 0, 1 power n. This is what we will mostly be focusing on, 0, 1 integer programs. Then you can treat each component of these as a probability and then try to get in a randomized fashion an integral solution. So this is what we call randomized rounding. One can think of these as being applicable in a very general context. So I will illustrate this in the context of 2 or 3 examples. Okay. So let me briefly give. So we know what is linear program. Okay. It is maximizing or minimizing a linear inequality and linear function on n variables subject to a set of linear constraints. We typically represent it in this matrix fashion. So A is a matrix of dimension m by n, and X is a vector, real vector, and P is a real vector, and C is also a real vectors. This is in Rm and this is in Rn. So this is what we call general linear program. Okay. So you have a set of m by n matrix. Each row of this matrix, when you take inner product with this n vector, will get you a linear inequality. And then you want to simultaneously satisfy all these m linear inequalities, and among all those solutions which satisfy these, you want to find a one which maximizes this linear function, either maximizes or minimizes depending on the problem. So this is the general framework of linear program which you all know. But several of the discrete optimizations problem that we focus on will turn out to be essentially these, except that this will be now restricted to take values only in, say, this or in this, and this turns out to be difficult. Okay. So ILP is basically this. Integer linear program is same as the general description of a problem is similar to this, except that you now restrict your solution space to be only in this or 0, 1 power n. some such thing, some finitely many possibilities. So here you could have infinitely, uncountably many solutions. Among them you have to pick one, whereas here you have only finitely many. But it so turns out that picking one among, the best among finitely many turns out to be more harder than picking the best among uncountably many. That is in the nature of. So if you recall, several of you have studied integer linear programming. So you all know that why this is true. So we can so how do you, so the question is, so let us now look at this a specific example of a formulation of a linear program. Let's take this independence problem. I'll come back independence set, independent set. So the goal is given a graph G. Okay. So it is not always possible. That is why I picked up this independence problem as an example. So what we are going to do, the randomized rounding works for a class of integer linear programs. Okay, I may not even be able to describe this class. I will illustrate this tool with the example of with the help of two examples and stop there. I don't think I will have time to elaborate on that. The general class of integer linear programs, some classes of integer linear programs where randomized rounding can help you to get good approximate solutions. Now if you take this independent set, given a graph G and an integer K, okay, you want to find an independent set, or is alpha of G at least K? This is your question. Does the alpha G stands for the maximum size of any independent set in G? So it basically asks whether does there exist an independent set of size K. This is what you want to know. And you can frame it as an integer linear program easily as follows. So what you do is, you want to maximize the size of an independent set. You give a 0, 1 variable for every vertex, subject to this constraint, xu plus xp is less than or equal to 1 for all uv and edge in E, and you restrict that all the vertices are either 0 or 1 for all u. Now you can easily see that every independent set, if you take any independent set, look at its characteristic vector, that is 1 if the vertex belongs to the set and 0 otherwise. The characteristic vector should obviously satisfy each of these inequalities for every edge. Okay? You can only pick one of these two, and they are all 0, 1 values, and the size you can calculate. Correspondingly, any integral solution or any solution to this ILP, okay, translates to, obviously represents a 0, 1 vector, which means an independent characteristic vector of some set, and that set that it represents will be independent because of this. If there is an edge with both components being 1, then this inequality will be violated. So it is obviously an independent set. So what you say is basically is that there is a one-to-one correspondence between the set of all integral solutions to these inequalities and the set of all independent sets, and hence when you maximize this, you are basically essentially finding the maximum size independent set. So obviously it is, this itself shows why integer linear program is NP-hard, even for such special types of linear programs which have only such special types of constraints like this. Now what we are going to say, not only this, okay, now the purpose is to show that the randomized rounding is that fractional solutions can be rounded in a randomized fashion to get good approximate integral solutions. Now this is an example where this will not work. So I will first give an example where it will not work. Now this is ILP. Now what about the computational complexity of finding this? Okay, this is, we know, is NP-hard. This problem, determining if there is an independent set of size at least K is NP-hard. Not only that, recent developments in this approximation problems show that this is not even likely to be approximable within any good ratio. Okay. So in fact, we can show that unless, I may be wrong in this, maybe Arvind can correct me, is this the complexity assumption for non-approximability of independence? Okay, okay, so I think if this is not true, then you do not have, there is no efficient algorithm for approximating alpha of g of an arbitrary g. So you don't assume anything about the input within a ratio of n power 1 minus epsilon, and this is true for any epsilon. Okay. So for every epsilon, however small it may be, you cannot hope to have an efficient algorithm for approximating alpha of g within this ratio unless some such thing happens. I may be slightly wrong in this, I don't remember exactly what is this complexity assumption, which is widely not believed to be true. Okay. So it is very unlikely to have good efficient algorithms to approximate independent set even within this ratio, multiplicative ratio. Now what about this? Associated to this is a thing known as what we call as integrality gap. So the integrality gap of a problem, integer linear program, is the following. Suppose you take a maximization problem like this, then you know the optimum value of this. You just relax this and allow it to take any value in 0, 1, between 0 and 1, any real value, you get what we call a linear program, or you are focusing on fractional solutions. Now, obviously, since you are enlarging the set of solutions, you will have a bigger value for the optimum. Now, how much this optimum can deviate, be bigger compared to the integral optimum, and that is known as the integrality gap. In this context, the integrality gap would be, you have the overall, as a function of g, overall graph, okay, of size n. Okay, you take any graph of size n and then take this, let me call this as optimum of g of LP by optimum of the ILP. You look at this and then you take the maximum. Even this maximum can become arbitrarily large. For example, if you take this independent set problem, okay, here is the ILP.
Arbitrarily large.
It can increase as a function of n. Yeah. So this is a function of n. Okay. Now if you look at this ILP, okay, you obviously have a solution where the vector x is just off everywhere. Okay. And this gives you a solution because if you relax this, okay, I am looking at the relaxed version of this. Half satisfies all of these inequalities, and hence optimum of the LP would be at least n by 2. Okay, at least n by 2. So it is not just for, it is true for any graph. For any graph, the fractional, you have a fractional solution whose cost is at least n by 2. Okay, and since this is true for any graph, we know that there are graphs where the independence number is bounded. Okay. So for graphs where the independence number is bounded, that is the maximum size of any independent set is bounded, you see that this, the ILP should naturally be bounded in its size for this class of graphs, whereas optimum ILP, so the value of the LP will be as large as n by 2. So this gap can become arbitrarily large. Now, can you think of an example of class of a graphs where this independence number will be bounded? Yeah? Huh? Yeah. No, independence number is bounded. Complete graph is one. Yeah. Yeah. Complete graph or more non-trivial class of graphs like planar graphs, complements of planar graphs. If you take a planar graph, then click size is bounded by at most 4. So if you take its complement, the independence number will be bounded by 4. So if you take the class of all complements of planar graphs, you have a huge gap between these two. So this, so as a result, since you are expressing this as a function of n, what you see is that as n becomes larger and larger, the gap between the optimum value of the LP and the optimum value of the ILP can increase arbitrarily large. And because of that, you cannot hope to, apply this randomized rounding technique to such class of problems. So that is what I initially promised. So you cannot say that I solve a LP and then randomize round, I will get a solution which cannot be too far below the optimum value of these. That is not possible. It is likely not possible. So now what we are going to do is look at some other class examples where it is applicable, and I illustrate this technique in those contexts. So one first example that one can think of is in general, what you mean by rounding, let me briefly illustrate this, explain this. So you have this solution. Suppose you have a solution like x1 plus x2 equals 3. And you look at this equality. And then you also restrict that x should be one of 0, 1 vector. Now how many solutions are there for this equality? So you have choose 3 solutions. You have choose 3 solutions which can have these. But what we can do is, one way to randomize is, this is not a good example. What I am trying to do is what we call a dependent randomized rounding. I am not sure if I will be able to touch this, but for the purpose of illustrating this randomized rounding, I will just illustrate. So one way to do this is that choose for all I set xi to be 1 with some probability, xi to be 1 with some probability, say half. Then what you get is, you will get an integer vector, and you do this independently for all I. Then you will get a vector. It will be a uniform distribution over this space 0, 1 power 5. But unfortunately, it may not even produce a solution. It may set all of these to be 1, so summing it 5 or summing to 3. But this is an example of what we call here it is not really producing always guaranteed to produce a solution. One can still make a guaranteed to produce a solution by repeating the experiment again and again. If the sum turns out to be either less than 3 or more than 3, you repeat this experiment again. You keep on doing this until you get a solution with this. And if you repeat this experiment until you get a solution which is equal to this, and then look at that condition probability space, then what you generate is nothing but a uniform sample over the set of all choose 3 solutions. That is because you started with the uniform sampling 0, 1 power 5. You condition it again and again until you get the solution which satisfies this equality. At that point, whatever that you get would all be uniform sample over this. But often what you have is, as we will see in examples later, that in addition to merely generating a random, so this is one way of randomly rounding, generating a random solution for this integral solution. Often what you may have to do is you may have to satisfy some extra constraints, that probability that the first variable is set to 1 is not, as we have assumed, uniformly off. You may be given some constraints. that x1 has to be set to 1 with probability say 3/4, x2 has to be set to 1 with probability 1/4 and so forth. So you have to generate a random sample satisfying all of these constraints simultaneously. The reason why we look at these is these turn out to be useful in getting an integral solution for some of the problems. So let me now illustrate this with one simple example, namely the minimum hasty cut. So the minimum hasty cut problem is as follows. You are given a graph G which is undirected. Okay. And you are given two special vertices S and T, and you want to separate S from T. Okay. So what we mean by separate, we want to find, so the goal is find a cut. By a cut we mean a bipartition of the vertices. Okay. Find a cut bipartition of the vertices such that, okay, S is in A and T is in B, and the number of which minimizes the number of edges. Number of edges across the cut is the set of is those edges which have one end in V A and other end in B. Okay. You want to look at those. So basically what you are doing is you are looking for a bipartition of the vertices into two pieces, say A and B, and look at the number of edges which go across the cut with one endpoint in A and another endpoint in B, and you want to minimize the number of such edges. Okay. Find a cut which minimizes these. So this is what we call the minimum hasty cut problem. So I hope the problem is clear. Okay.
A intersection B is empty or?
Yeah, bipartition. When I say partition, it means that partition. So the parts don't have anything in common, and their union is A. Okay. Now we have seen, for those of you who have studied this randomized algorithms course, you know there is a efficient algorithm to produce this minimum cut. Now what we are going to look at this is a formulation of this as an ILP program, integer linear program, and apply randomized rounding to that. That will illustrate this concept of what we call randomized rounding. Now, so the goal is now clear what we want to do. Okay. So naturally one can translate this into a linear integer program as follows. So associate, so you give a variable x to every vertex in the graph, and if it belongs to A you associate it with a 0, and if it belongs to 1 you associate it with B. And then you have to express the number of edges that go across them. So let's attempt one such formulation. So what you want to do is you want to minimize. So we are looking at a minimization problem. Minimize the number of edges that go across the cut. Okay. So which means you will try to identify some 0, 1 variable with every edge. Okay. So let me call this, for every edge in the graph, okay, you have ZE. Okay. Then in fact one can even generalize this as follows. We can even assume that there is a cost function associated with every edge. Let me look at this as some R plus. Okay. Cost function. So you want to find a minimum weighted cut. So in that case this will not be the minimize the number of edges, but minimize the total weight of the edge cut. That is sum of weights of all edges in the cut. This is what you want to minimize. Okay. So in that case, if you decide to include this edge as part of your cut, then you have to multiply it by its weight. So you have CE. Okay. You want to minimize this function subject to what you want? You want the following. Basically, the cut is essentially decided by the bipartition of the vertices. So naturally, you tend to give 1 or 0 variable for 0, 1 variable for every vertex. And then what you have now, this is the crucial part. What you have to do is now, how do you translate? So we know that if an edge crosses this cut, okay, I know that I have decided to identify A with 0 and B with 1, and suppose UV is an edge which crosses this cut. I want to capture this fact that if these two vertices, when will it be a cross edge? It will be a cross edge only if the two endpoints get opposite polarity, 0, 1 or 1, 0. So from these two values, I should get this value. Okay. So how do you get it? So one can say that Z is, you just take the absolute difference between X and V for all E V in the graph. Okay. You just look at the absolute difference. Okay. If both of them endpoints U and V fall in the same part, then obviously the difference would be 0 and this will be 0. And it will be 1 only if one of them gets 1, the other gets 0. And hence one can use this. Obviously, as a result of this, it automatically implies that GE would be 0 or 1 for all E. And it obviously minimizes this cut. This, I don't claim this is integer linear program, but this is some formulation. Let's first look at this formulation and convince ourselves that it indeed captures the minimum cut. So what is a minimum cut? It's basically a bipartition, which minimizes the total weight of all edges across the cut. Then basically what it does is you can associate this with the 0, 1 vector, having 0 with for vertices in A and 1 with vertices in B. And for every such cut, GE becomes 1 if and only if it is a cut edge. And for other edges, this becomes 0. So here you are calculating only the weight of the cut edges. So every 0, 1 solution of XUs gives rise to a cut. And conversely, so there is obviously an injective mapping from 0, 1 vectors here to cuts here. Okay, modulo this the modulo a permutation of the cuts in the sense that A can get 1 and B can get 0. Okay, permutation of the parts. Conversely, if you take any solution to this, okay, obviously that gives rise to an integral solution, and the variable ZE obviously captures all of these. So you have a one-to-one correspondence between 0, 1 vectors here and the set of all bipartitions. Okay. What about we want both parts to be non-empty. We need to ensure that. So for that we need to add that XS should be 0 and now we are introducing XT should be 1. Okay. So both parts cannot become, any of the parts cannot become empty because you are explicitly ensuring that there is a 0 part, there is at least one element in the 0 part and at least one element in the 0 part. Okay. Now, so this is what we want. We want S to be present here and T to be present here. Okay. You have got this. And you obviously have a one-to-one correspondence between the set of all ST cuts and set of all 0, 1 vectors satisfying these two additional constraints, inequalities. And obviously the ZE, this function, when ZE is defined in this way, captures this. That is also clear. So it works fine. It is an integer linear program except for this equality. This is not really a linear function of the two variables XU and XV. I said that linear programming is that it should be a linear function. One way to overcome this is replace this as follows. G is at least xu minus xv and G is at least xv minus xu for all EUV. Okay. Now I claim that this GE would capture this in any optimum solution. Okay. Let us look at this. Let us first initially focus on 0-1 solution. When you have 0-1 solution, then certainly either both of them are equal. In that case, these would be zeros. So GE. Now in addition to this, if I replace this by this, I have to explicitly add GE equals 0 or 1 for all E. That extra concern I need to add. Okay. Here I didn't need to add because it was obviously implied by this. So I add this. When I add this, now I know that G lies either 0 or 1. Okay. In addition to this, I explicitly mentioned that it should be at least this. If both of them take the same value, then this would become 0. And G has two possibilities, either 0 or 1. On the other hand, if they take different values, 0, 1 or 1 and 0, then the maximum of these would be 1. And since it is at least the maximum of these two, it will take 1. So there is no problem as far as cut edges are concerned. For cut edges, that is those with one component 1 and the other component 0, surely GE would be set to 1. There is no doubt. What about non-cut edges? If both of them happen to be equal, say 1, 1 or 0, 0, then this would be 0, both sides would be 0, and hence this could be any non-negative value. Since we are restricting GE to be 0 or 1, it could take one of the two values 0 or 1. But in an optimum solution, it will not take the value 1 because you are trying to minimize this. So why do you want to make GE 1 when you can as well use 0 satisfying these inequalities, thereby reducing this. So what we get in any optimum solution of this, so I have removed this constraint and replaced it by this. G is 0 for all non-cut edges. And hence this captures exactly the set of the optimum solution, all optimum solutions. Okay. So this is what we call an integer linear programming formulation of the minimum cut problem. Okay. Now what we are going to do is, now we are going to relax this. Look at the fractional program. Okay. So relax the ILP. For ST minimum cut and solve it and get an optimum solution. Let me call the optimum solution as something like, say, XU star and Z star. So U is in V and V is in V about this. Okay. Now, since 0 x, so what we mean by relaxing, we now what it means is that the values XU and ZE will now lie only between 0 and 1. This is what with the relaxation. What we are going to do is, now we are going to use this, and obviously with let me also write the optimum value of LP. Let me denote it by some K. Okay, let me denote it by some K. Then what we are going to do is the following. You have the 0 line, 0, and then you have 1. You choose uniformly at random. Okay. choose uniformly at random a real number R between 0 and 1. Okay. The left closed and right open interval 0, 1. Okay. Now, I will also mention right here that I am not going to discuss about realizing these choices. Okay. So, that is a different issue altogether. Okay. How are you going to choose these random values, or in later future thing you will be talking about setting a variable xi with probability xu. How are you going to realize this probability choice? Okay. So how to choose set a value 0 or 1 with probability bias xu. How are you going to realize this? All these I am not going to discuss this now. Okay. So it is, I will be focusing mostly on the theoretical aspects of this. Okay. So choose a random value or 0 uniformly between these, and then this is the following procedure for randomly rounding the fractional solution that we have got into an integral solution. So let me let xu be 1 if xu star is less than or equal to R and 0 otherwise. Okay. So we now have to convert this into an integral solution. The integral solution is 0, 1 vector. That is the procedure that we describe here. For every vertex u, if you set it to 1, if the corresponding value xu star, you compare it with the randomly chosen, and this is uniformly at random over this, and see if it is at most R and set it to 0 otherwise. Okay. Now you obviously get a 0, 1 solution. Now we claim that this 0, 1 solution, the expected value of the 0, 1 solution, if you look at the expected value of this, that would be exactly equal to the optimum of the relaxation of the LP, that is key. This is basically, okay. So we know that optimum of LP is at most the optimum of the ILP, because it is a minimization problem that we are looking at. And optimum of the ILP is exactly equal to optimum or minimum optimum ST cut size. Yes, that is how we define the ILP. Okay, now as a result, what you get by standard arguments in probabilistic method, if you can show that the expected, you get an integral solution. Now any integral solution defines a cut. You look at the expected weight of the cut, the expected weight of the edges across the cut. We are going to show that that expected weight is exactly equal to this, which means there is a 0, 1 solution. Okay, there is a 0, 1 solution whose size is at most this. But then integral solution size cannot be better than the optimum of the fractional solution, and hence it would be exactly equal to this. So you get an integral solution. This is the basic outline. So now let us look at this. xu equals 1 if xu is star is at most R or 0 otherwise. Then what about the weight of the cut? The weight of the cut would be, if you look at the total weight of the cut, it would be nothing but you look at all the edges E such that xu is, I have defined this to be x, capital XU is not equal to capital XV and CUV. This is what we have. Okay, we are basically counting the weight of all these cuts. As a result, now let us look at this. We have this. What is the expectation of this cut that you are talking about? Okay. Now I will introduce it as follows. I will introduce a random variable. Let me call this random variable as Z. Z is 1 if E is a cut edge and 0 otherwise. Okay. So you get a random cut, random discrete solution. With respect to this random discrete solution, you define another random variable. I define it in this way. Okay. Now what will be the weight of the cut? Weight of the cut would be basically then Z over all E, because those which are, for which these two are equal, they should not be counted, so obviously they will not be counted. ZE would become 0, otherwise they should be counted, and CE is 0, so you have to have CUV. This is what you have. Okay. So this is the total weight of the random cut that you have here. Now what is the expectation of this total weight of the random cut? Expectation of the weight of the random cut is expectation of this summation, which by linearity of expectation can be reduced to E CE times expectation of Z. This is what we have. Okay. Now what is expectation of ZE? If you look at this, you look at this. What is E? Suppose E is an edge which joins vertices U and V. You want to determine ZE is an indicator random variable 0 or 1. So its expectation is exactly the probability that Z equals 1. So when will the edge UV will become a cut edge? Only if, so you recall, when do you said it will become a cut edge if one of them get 1, the other gets 0. Okay, one of them gets 1 and the other gets 0. Now you look at these XU, XV star, they lie on the real line 0 and 1 somewhere here. Without loss of generality, let us assume that XU star appears before it is smaller than XV star. Okay, then the edge joining U and V will become a cut edge, okay, only if R chooses a value which lies exactly in this interval, XU star or closed here, but XV star open here. Okay, why? If it chooses a value, if XV star comes before XU star, it will be similar to this. In essence, what it means is this will be 1 only if what you have is that R, the random value that you choose. So we know that there are two possibilities. Either they are equal. If they are equal, then the interval became an interval of 0 length. In that case, both will get 1 or both will get 0. That is what it will happen. In that case, it will not be counted towards this probability. Or they get distinct values. If they get distinct values, then you have to choose the value, random value R, to lie somewhere in this off open and off closed interval. Okay, that is exactly this requires that R should lie somewhere in this. It should be minimum of XU star and XV star and maximum of XU star XV star open. In other words, this would be essentially, it is determined essentially by the length of the interval. So it is exactly the length of the interval XU star minus XV star. This is what is determining it. Okay. So what is then this probability would be summation over E CE, expectation of ZE is exactly equal to this. But what is XU star minus XV star? You look at optimum solution. In the optimum solution, okay, in any optimum solution, GE has to be said to be exactly the absolute difference between them. We know that it is at least the absolute difference. That is what these two inequalities tell you. If it is more than the absolute solution, then it will not be an optimum solution, because you can bring down the solution value slightly less by bringing down GE and make it coincide with the absolute difference, exactly the absolute difference. As a result, this probability is exactly absolute difference means it is basically, what is this? It will be nothing but the Z star. Okay, in the optimum solution it will be nothing but Z star, this probability. So it is Z star. But what is summation over E C Z star? It is exactly this optimum. Okay, so optimum of the LP. So what have we established? From a given fractional solution, optimal fractional solution, we have described a way of rounding it in a randomized fashion to a discrete 0-1 solution, such that the expectation of the total weight of the cut described by this 0-1 solution is exactly equal to the optimum of LP. Now there is a very familiar principle in probabilistic method. For the entire probabilistic method relies on this simple but powerful principle, that is that you have a probability space and you define a random variable over this probability space, and if the expectation is equals mu, then these two statements are true. There exists some point in the probability space such that value of the random variable over this probability space is at most mu, and one can also make this statement, value of this random variable is at least mu. So you have a point for which the value of the random variable is at most mu. Surely this happens with positive probability. This is a statement which holds true. And you also have a point in the probability space for which the value of the random variable is at least mu. These two statements are true. Now one can apply this. This is easy to see in the case of discrete probability spaces. Okay. What is discrete probability spaces? You have a finite set, finite or countable set, and you introduce a probability distribution over this space, and then define this expectation, all this. It is easy to see there. But what we have here is a continuous distribution. The underlying experiment is choosing uniformly at random this. Okay, it is a continuous random choice. How do you reduce these easily from this? Okay, you can see this by observing the following. What you notice is that the value of R, okay, as you have the value of R, you choose uniformly at random, you have a random value between these. As R keeps going from 0 towards 1, and if you look at this function, okay, what happens is this value, okay, the total weight of the random cut is this, okay, total weight of the random cut is this, okay. Yeah, Z is an indicator, random variable, which is an indicator random variable, which is defined by these random variables xu and xp. What you can see is that this total weight of the random cut does not change at all, except at only a finitely many number of points. In particular, it will change it at most n times. Why? So you write down the values of all the xu star in increasing order. Okay, look at the first xu star, the smallest one, below which everything is, all the value xu star are above this value of this, and hence they will all be 0. For all these variables, it will be xu would be 0. So you get one particular cut. No, you will not get. In fact, we set xs to be 0. So s will always be set to 1. S will always be set to 1, but everything else will not be part of. So you get a cut where you get a bipartition where S is the only element and everything else is in the other part. As you keep increasing R, it remains the same. When you cross the first xu star, the smallest one, it is at that point that the function value can change, possibly change. It depends on the structure of the graph. And then after this xu star, if several of them are identical to this, then again there is no change. You now look at the second smallest xu star. It remains the same until you reach there, and then it changes only at that point. In this way, what you see is that this function that I talked about, total weight of the random cut, the value of this, as R keeps increasing, this value keeps changing, but it changes only in the following fashion. It remains constant over some interval, and then it either goes down or goes up depending on the structure of the graph and the optimum solution, and then it goes up or goes down and so forth. So what you see is that even if R is chosen uniformly at random over a continuous interval, the object of interest, namely XU's and ZE's and these, in particular this random variable, total weight of the random cut, it does not take continuous values, it takes only finitely many possible values. Since this is only a finitely many possible values, and our argument is in terms of the expectation of this random variable, okay, so the random variable under consideration takes only finitely many possible values, and hence you can easily apply those arguments and deduce that there is a point in the probability space. That means there is a particular value of R for which, okay, the expected weight, the weight of the random cut that you get is at most optimum of LP. But there is a discrete solution. So if it has to be at most optimum of the fractional solution, it means that they are equal. Okay. So you get a, so what does this prove? It not only shows you how to get a discrete solution by using this procedure, it also shows the following important thing, that as far as this problem is concerned, the integrality gap is 1. The fractional solution and the integral solution, the optimum fractional solution and optimum integral solution, they both get the same value. Okay. So the purpose is mainly to, so this is an example of what we call a dependent randomized rounding. Okay. So what do I mean by dependent randomized rounding? XU's are set to 1 or 0 in a random fashion, and these 1 or 0 determine the discrete solution that you are talking about, but they are not set to 1 or 0 in an independent fashion. They are all decided by the random value of R that you choose. Okay, in that sense, they are all dependent on one another. Now, there is another example of dependent randomized rounding that I wrote down before. X1 plus Xy equals 3. Okay, so you are looking for a random solution of this equation X1, X2, X3, Xy equals 3, and it is dependent in the sense that the values, the random variables X1 through Xy cannot take independent values independently. They are constrained by the fact that they all should sum to 3. Okay, now I will illustrate. Can I take another 15? Now I will illustrate another example where randomized rounding can be used to in fact get so this is what we call as multi-commodity flow. Okay. So, yeah.
The previous example, x1 to x5 equal to, the thing that using a randomized algorithm, you can count the number of solutions to that.
Where?
X1 plus x5 equal to 3. The claim is that using randomized algorithm, you can count the number of solutions to that because what is the objective?
That was a toy example I picked up, but I realized that it involves dependent randomized rounding, so I didn't elaborate further. No, I didn't talk about random objective function or any of these. Okay, it is just give you how a fractional solution can be converted into an integral solution. It is for that. So nothing. Don't pay much attention to that example. So it is just how a fractional solution can be used to convert. So I will give now a little more concrete example of this. Okay. So what? So here the problem is as follows.
Just one small.
Yeah.
Do all the min ST cuts show up this way? Because we know that there are only n square of them.
Yeah.
To the other algorithm.
Yeah. Yeah.
Do all of them show up?
All of them show up. Yeah. It's a
Count them.
good question. Do all of them show up?
There in the randomized
So it,
algorithm, there you will find any one of them.
yeah.
Random.
Yeah. Uh, no, I think it will be decided by the optimum fractional solution that you get. That will dictate the kind of optimum cuts that you will get.
So we can't conclude
I don't
about
think
the
we can
number.
control. No. No, the purpose is not to even optimize, or it is just that how an example of how randomized rounding can be used to convert a fractional solution to an integral solution. No, I don't think one has to think about it. I don't think one can answer this question.
It just occurred.
Yeah, it will depend on the structure of the solution, optimum solution that you have, and we know that at least one minimum cut is there. That is what we can say as of now. But I think little more thought can reveal some estimate on how many cuts can be.
Here also another thing is there could be multiplicity could be same of many integral solutions. Even then we need to calculate.
Multiplicity of?
Many, what is it made of the same value there?
Yeah.
Then we'll have to. Does it mean that you always put all of them in one side, or can you?
Yeah, if several U's are there such that they all get the same XU star, then they will all go to the same pot, either A or B, depending on the choice of R.
This need not be the case in every.
Huh?
This need not be the case in every min cut. I mean, there could be min cuts which separate them. Possible. Right.
No, I don't think one can say that any two vertices are separated by a min cut. That we
That's
cannot
not
say.
what I'm saying. Possibly. Here you will not, because you will treat them all together.
Yeah.
But there could be some min cuts which you will miss out because of that. That's not-
Yeah, what you say is true. If there is a minimum cut in which U and V are in two different parts, and U and V are in two different parts, of course, it will not. Obviously, this shows. Okay, so the idea is you have two different minimum cuts, then they will differ on at least one edge. Okay, should they not differ on at least one edge? Because once you specify the cuts, that uniquely defines the partition. So if there are two different minimum cuts, they should differ on at least one edge. And if your optimum fractional solution is such that it assigns the same value XU star, XV star to both endpoints of these, then that particular cut in which they appear in different parts will not show up here. Okay. But it is not clear if optimum solution assigns the same value. It is not clear. So we cannot say that it will not generate or it will generate. A little more thought has to be given to it. Okay, so now the multi-commodity flow problem, you have the following. You have an undirected graph. And you have k commodities, k, let me assume for k unique commodities. Okay, one can think of this undirected graph as some kind of a network through which you are transporting these commodities. By unit commodity, I mean something like a huge container or something. And these commodities have destinations, SI, TI, for them. Okay. And the ith commodity should be shipped from source SI to its destination TI. And it is what we also call unsplittable. Let's focusing on unsplittable multi-commodity flow. What it means is the commodity cannot be split. Okay, it has to be transported as a single unit. At no point you can split it, which means it is essentially reduces to finding a path between Si and Ti. That is what you need to do. You have to flow it from source Si to Ti along the edges of the undirected graph. So you have to find a path from Si to Ti, and you have to find a path for one for every such Si, such that what you have to do is you want to minimize the amount of congestion along any edge. Okay, so the goal is find a path Pi from Si to Ti for every I, such that for any edge E, the congestion of E defined to be the number of I such that E is in Pi, E is minimized. Okay. For any edge E, you define it in this way, then maximum over all E in the congestion of E is minimized. This is what you want to achieve. So for a given assignment of paths to the commodities, you define what we call as congestion of any edge, the number of paths that share this edge. So it reflects in a sense that the amount of time that the commodities have to wait to get transported along this edge, or it can also reflect what we call as the bandwidth or the capacity of the edge to transport so many commodities along its path. So I'm not going to dwell too much onto the physical interpretation, but if you focus on the mathematical interpretation, basically it is the number of edges, the number of paths that you are assigning that share this edge. We want to minimize this value of E. No, you look for any edge, you define this and then take the maximum congestion along any edge for this assignment. That is what we call the congestion of this path assignment. You want to find a path assignment which minimizes this maximum congestion. So this is the goal. Now this is something which you can see as okay. So now let us look at this problem. How do you formulate it? Okay. Now it will be helpful to convert this into a directed graph and view it as a directed graph and then derive the arguments. So what I do is I replace each undirected edge UV by two directed edge UV and VU. Okay. And then for source vertices, I always So no, I was just for source vertices, I will always direct all edges incident on it as outgoing arcs. Okay, but the only problem that might arise is if some vertex happens to be both the source and sink, source vertex for some commodity and sink vertex for some other commodity, then anyway you are replicating all edges with two copies, one indirect and one indirect thing, so that takes care of that. Okay, yeah, no, source vertex also you multiply, you duplicate every edge in this fashion, so there is no need to, it automatically takes care of it. Now what we have is, having done this, now you formulate an integer linear program as follows. So basically what you want to do, you want to, let us first focus on integer linear program because that captures exactly the discrete solution that we are looking for. So what are the characteristics of a solution? A path say, it originates at the source Si, picks an outgoing arc and then keeps on picking, goes on picking an outgoing arc at every vertex and finally it reaches the sink vertex Ti. So what you see here for this path, for every intermediate vertex in the path, there is exactly one incoming arc and exactly one outgoing arc. Okay, and for source vertex there is only one outgoing arc, and for the sink vertex there is only one incoming arc. These are the characteristics that you see. So you can say it as follows: an arbitrary edge is part of the path Pi. You can indicate this by an indicator random variable. Okay, so what you do is, for all subject to, you introduce a variable Fi of E. So if an arbitrary edge is uv, I now replace every undirected edge by two directed edges, uv, vu. So for any uv, what you have is Fi of uv is 0 or 1 for all I, for every commodity I, and for all undirected edge uv. So similarly you have v to u, that is also there. So these are the discrete random variables, not random variables, discrete values that we are focusing on, and these should satisfy the following constraint, namely that for any vertex, for all commodities I, if you look at any directed arc edge uv, you want that Fi of, you look at for all I and for all u, for all v such that uv is an outgoing arc, you want this to be equal to 1. Okay, there is exactly one outgoing arc incident at u along which the commodity should flow, because it is an unsplittable flow, so it cannot split between arcs. So this should be true. Not only that, we also want the same thing for all incoming arc, for all v such that vu is an arc. Okay, it is u2. So this takes care of this, and then you have to have this for all I. Okay, you have v such that Si of v, Fa of SIV should be 1, and you have v such that you have v to Ti is an arc, Fa of v to Ti should be 1. This should also be satisfied. So there is exactly one unit of the commodity, one whole unit of the commodity that should flow out of ith commodity, that should flow out of the ith sink source vertex, and similarly for sink vertex. Okay. So this takes care of the, and this should be true for all u not equal to S and T. You want this to be. So for any vertex other than S and T, any commodity that flows into that vertex should get out of that vertex, unless it is happens to be one of the source or sink of one of the commodities. So for all I, now let me put it precisely, write it, for all I and for all u which is neither the source nor the sink vertex of this commodity, this should be satisfied. And for the source and sink vertices, this should be satisfied. Okay, this clearly specifies a path from Si to Ti for every I. If you are able to find a 0-1 solution which satisfies these, it specifies a path, okay, the directed path that we are looking at here. And what do we want? We want to find a path which minimizes the congestion. How do you capture the congestion? Congestion can be captured in this way. One is that, so since you are using an edge in both ways, it can happen that some commodity might be passed along in the direction u to v, and for some other commodity it can be passed along the direction v to u. Both of them, for undirected edges, both of them will contribute to the congestion. So the congestion of the edge, for any edge, the congestion is, okay, for all Fa of uv over all I Fi of Vu. This is the total congestion with respect to this discrete solution. Okay, and what we want? We want to minimize this. We want to minimize this, so we specify it by introducing another variable, call it C, and then your goal is to minimize C. So minimize C subject to the following. Okay, there is an upper bound on the congestion of any edge, and these constraints specify, these constraints together with the 0, 1 restrictions specify a path, and this specifies the congestion along any edge, and you want to minimize this congestion. Okay. Now, this is the 0, 1 integer programming formulation of this multi-commodity flow. What you now do is you relax it. Okay, you relax it and solve the fractional version, relaxed version. So relax and solve it. To get an optimum fractional solution. Let me denote the fractional solution by some other variable. So GA of UV and C star. Okay, this is the fractional solution that we get. Okay. By relaxing, what you mean is you are allowing the variable not necessarily to be 0 or 1, but anywhere between 0 and 1. Okay. And then we are now going to apply randomized rounding as follows. When you allow relaxation, what happens is, relaxation means you allow the variables Fi to be anywhere between 0 and 1. All that is required is that they should satisfy this. As a result, what you may get is that the commodity would be splitting. So relaxation nothing but allowing the commodity to be split between edges. So what you get is, if you focus on any particular commodity, these constraints, if they are restricted to be 0 1 variable, specify a unique directed path. Here, instead of a unique directed path, it specifies a directed subgraph. So the commodity gets split right at the source sink and gets split into pieces, and then finally it manages all of them to get assembled at the sink. Like water starts from the source and finally manages to reach some sink. Okay, so it does that. What we are now going to do is, we use randomized rounding procedure. Now before we do that, what we are going to do is, we are going to apply a technique that is called as path stripping. By applying this, we are going to convert this fractional solution associated with any, so for every I you get a fractional solution. That is what we have. We have defined a variable Fi for every I. So let's just focus on one particular I. It defines a fractional solution. From this fractional solution, you get a set of discrete solution. What is a discrete solution? A directed path from Si to 2A. So you get a set of discrete solutions by an argument known as path stripping. So to you get Pi. Pi is a set of paths from Si to Ti. In addition, what you do is, you also define what is called a weight of a path. Weight of a path, okay, such that if you look at this weight, now you get a collection of paths and you get a weight from each of these to 0, 1, such that if you sum all the paths and their weights, weight of every path, that would be 1. Okay, you get a collection of discrete paths, and every path will get a weight a non-negative weight lying between 0 and 1, and if you sum all the weights of all the parts, these will be a finite set, it turns out to be 1. So this naturally gives you a interpretation of treating this as a probability distribution. The weight can be thought of as a probability distribution defined over the set of parts. Okay. Now we will use this probability distribution to randomly round. Okay. Now before I describe how you get a collection of parts in this way, we will first assume this is true. So what is the point here? The point is you get a collection of parts Pi, and this is true. In addition to this, we also have this. What is that? It is not just an arbitrary distribution, it is a distribution which was dictated by the fractional solution that we have here. So in addition to this, these parts also satisfy the following condition, namely for all edges, undirected edges in the graph, if you look at those P such that E is in P and you look at its weight, okay, you look at all the parts, we are now, from now on we are going to focus on one particular I and argue with respect to that. So you look at all the parts in Pi, and among all those parts, look at those which contain the edge E, look at its weight. This weight would be exactly equal to Fi of E. What is Fi of E? I have not defined. Fi of E would be basically the congestion, total congestion in both directions. So we can define it as Fi of E, the undirected edge would be Fi of UV plus Fi of V. This is what you get. Okay. So this is what you do for all I. Now the randomized rounding procedure is simple. The procedure is as follows. For each I, choose P randomly from Pi, let me call this Pi, randomly from Pi as follows, subject to what is the probability that you pick some particular I, that would be exactly the weight of the path. Okay. PA is a collection of, finite collection of paths. You randomly pick one such path. What is the probability that the random choice PA is exactly equal to the some arbitrary fixed path? That probability is exactly equal to its weight. Basically, it's basically defined by this distribution. Okay. And these randomized rounding, that's it. Okay. So what you have is, for every commodity you have obtained a finite collection of paths, and you have also obtained a distribution over these paths, and this distribution in addition satisfies this condition also. Having done this, the randomized rounding is simply this. Choose Pi for every path, for every I you choose a random path from Pi, script Pi, this is small Pi, okay, in this way. Now let's look at the congestion of any weight, okay. So you fix any edge, any. Okay. What is a congestion? Congestion, so what is the expectation of the congestion, okay. Let us focus on that. Once we are able to focus on the expectation, we can then apply known concentration inequalities. So what is the expectation? The congestion at E, okay, is basically you introduce a random variable ZEI, okay, which is 1 if E belongs to PI and 0 otherwise. Okay. You have got a random collection of paths, one for every I. With respect to this random collection, you define indicator random variable for the edge E. ZEI. It is 1 if E belongs to the random path chosen for the ith commodity and 0 otherwise. Then what will be the congestion? Congestion will be the sum of these indicator random variables. So congestion at the edge E, summation over E ZEI, and hence the expectation of this congestion would be the expectation of these. But what is the expectation of an indicator random variable? It is the probability. So for ZEI, it would be, if E is chosen, part of the random path that you choose, the probability that E belongs to the random path is exactly this. Okay? It is the weights of all those paths which contain E. It will be chosen with this probability. It is because these W define the distribution that we are employing here. And we know that the distribution is such that this is satisfied. So this is summation over all I, it is Fi of E. That is also known. But we know that Fi of E over all I are upper bounded by this value, because Fi of E is the sum of these for every I, and it is upper bounded by C. So in this case, we denote the optimum solution by this, so it is C star. So this is what we have got. So what we have established is that for any edge E, the expectation of the congestion with respect to the random choice of paths is at most C star, where C star is the optimum fractional value. Okay. Now if you look at the ZEI, they are all independent random variables, because these are decided only by the random choices involving the ith commodity, and these choices can all be made independently. So since PAs are chosen independently for different I, ZAs are also independent, so it is sum of independent indicator random variables. And for sum of independent indicator random variables, one can apply well-known bounds known as Chernoff bounds, which express the deviation from the mean in terms of an exponential function involving the deviation. Okay, and if you apply that, one can get an upper bound on these. Okay, let me quickly explain that and then finish that. But one catch here is that these FAE do not sum to exactly C star. If they sum exactly to C star, one can directly get it in terms of C star. Rather, they sum to something which is at most C star. Okay. But still, one can handle it as follows. C star, one can think of these by considering another set of indicator random variables which stochastically dominate these, in the sense that for every such random variable, its expectation is at least as large as the expectation here, and its total mean is exactly equal to this. In that case, one can prove that probability that this takes a value which is twice C star is upper bounded by the probability that the dominating sequence of random variables takes a value at least twice C star. Because if you have two sequence of independent random variables, okay, let's assume for sake of simplicity that you have one coin whose bias is say 1/4, and you have another coin whose bias is half. Then suppose you repeat the coin with bias 1/4 10 times, and you also repeat the coin with bias 0.5 10 times. Then you ask the following question: what is the probability that the first sum is at least some value? And you also ask the question: what is the second sum is at least something? Surely the probability for the second sum is larger. So what it seems is, as a consequence, probability that what you get as a congestion of E, because the second sum is the sum of indicator random variables, each of which have a higher probability of being set to 1. And if we can upper bound that sum, upper bound the probability that that sum is at least something, then surely that probability upper bound also applies to the first sum, which is a sum of indicator random variables with smaller expectations. So as a result, this is not really a big issue, one can handle this. So we will assume that they are equal to exactly, By that argument, what it means is, what is the probability that the sum of indicator random variables whose sum is exactly equal to C star is by Chernoff bounds, one can show that the probability that it is at least 2 C star can be upper bounded by e power minus omega C star. This is what you get. Okay. This is true for any E. We fixed any E. Now, if you choose C star to be at least say phi log n, then or some sufficiently large constant d log n, then what we get is that probability that there exists some E such that congestion at the edge E is at least 2 C star is upper bounded by some very small value. It goes to 0. One can ensure this. So what do you get? For those problem instances where the optimum congestion, see these C star is the optimum value of the fractional solution, and optimum value of the integral solution is at least as large as optimum value of the fractional solution, and hence for those integral problem instances where the optimum value of the integral solution is reasonably large, or the optimum value of the fractional solution is reasonably large, something like d log n, what you get is, one gets that the probability for any fixed edge E, the congestion can be upper bounded by something like 1 over n cube or 1 over n squared, and hence when you apply union of probabilities, you can reduce that for the probability that there exists some edge for which the congestion is at least this much can be upper bounded to be very small. It goes to 0. So what do you get? You get a solution, an integral solution, for which the congestion is not more than 2 C star. So you get a 2 approximation in that case. Okay, provided we assume that C star is at least d log n. I think. Okay. So this is a very. I'll quickly take 2 minutes to illustrate this. The path stripping is an argument. Basically, what you do is you look for a path by standard network flow arguments. You basically, what it means is you know that there is a flow of 1 unit from the source to the sink, Si to Ti. What you do is you form a directed graph in which you ignore all those edges for which the flow along for the ith commodity along that directed edge is 0. So what you get is a smaller directed graph, and since there is a flow of 1 unit from source to sink, there should exist a path. You pick one such path, and then in that path you find the edge for which at least one edge can be, you find the edge of least flow value along that, and then you saturate that edge. That will take care of establishing at least one edge. Basically what you do is you find a path and find the least flow value along that path for this commodity, and then assign this flow value along this path. That will saturate that edge, and you remove this path along with you remove not this path but those edges which are saturated, and you keep on doing this. In every iteration you remove at least one edge. Each time you get a path, finally you will end up getting a collection of discrete paths. Okay, sure. Yeah, you wanted to ask? Oh, sorry, I took more time than what I